Okay, so here we go. Here's where we were last time. Oh, well, before I get into the math, so just a reminder, today's Friday, right? So we have a test on Monday. So, best to everybody for studying over the weekend, etc. Recall that the fair game material is indicated on the class schedule. And in particular, what we cover today is not fair game for the exam. However, it is fair game for exam 3, and that's not that long from now, so you got to keep that in mind as well. Okay. Oh, and then let's see here. I believe it is true that the homework due dates are adjusted slightly from the usual pattern in recognition of the fact that we have an exam on Monday. And I don't remember the exact specifics, but anyway, just do pay careful attention to the listed due dates on the class schedule. I think I gave you all a little bit of a delay in recognition of the exam. Okay. All right. So back to where we were. We were looking at symmetry arguments. One of my favorite integration techniques, because even though it might not apply super often, when it does, it's just crazy powerful. Right? So here's another example, looking at this domain right here, and you can see that if I were to consider this integral in rectangular coordinates, or by usual methods, you're going to hit corners. Right? And you could even imagine, hey, maybe I'll use my newfound knowledge of change of variables to rotate this shape one way or the other. Well, okay, but that is also additional effort, and you're still going to have non-constant bounds. So that's not super either. Okay. Plus that'll introduce, well, anyway, so so there's a lot to, that's not an immediate problem solver either. So the big idea is that you look at this domain, and you can notice without too much trouble, if I can do artistically competent, you'll notice that there is a line there, and this domain is symmetric over that line. So we're halfway to a symmetry argument already. Everybody see that? That's something you always want to keep a lookout for, because it comes up surprisingly often. Okay, now of course we do need to know that the integrand is odd. Sometimes it's pretty clear how that works. For example, looking at this example back here, we realized we were reflecting over the y-axis. It's pretty easy to write down what it means to reflect over the y-axis. Specifically, you get a minus sign just on the x-coordinate, and we note that when you pop that in to this function, you can just see every term becomes the negative of what it had been, right? So sometimes it's just kind of clear. But sometimes it's not. And so I like to use this example as an opportunity to point out different ways that you can write down reflection formulas. I suppose in general you could just use your general knowledge of linear algebra. Reflections over the origin anyway are always linear transformations, and therefore you can talk about matrices and images as standard basis vectors. Sure, right? But sometimes there's easy little foots in the door, and having noticed that we're reflecting over that line, right, and drawing a quick picture of what a reflection looks like so, it doesn't just leap off the page at you exactly how that geometric process of reflecting over that line, how does that manifest itself algebraically, right? It's not immediately clear. It's not a rotation. You're not taking the negative of the vector. Something weird's going on, right? So what I wanted to point out to y'all is y'all can realize how this reflection works by looking at what I like to call a little rectangular frame for that point. And so in particular, that edge of this little rectangular frame, being as it is parallel to the x-axis, and the line we're reflecting over is 45 degrees, right? It is a pretty easy argument to see that its reflection looks like that. Right there along the y-axis. That part's easy. And then likewise, this bit here, being vertical and reflecting over a 45-degree line, its result is horizontal. So you can then just read straight off of this picture, and you can just right there, you can see what the first and second coordinates of that reflected point are, and there they are. And so anyway, nice little trick. The big idea here is that when you're looking at a 45-degree line, look at a rectangular frame for the point, and just kind of copy the results. Okay. All right. So with that noted, now there is a little bit of work to be done. And again, per my policy, you don't have to show this work, but if you want to protect yourself against the possibility of making a claim that isn't true, certainly in this case it's not obvious, right? The way that you will that you will confirm for yourself that this function indeed has the odd symmetry that is essential to make a symmetry argument, all you have to do is plug the reflection in to the function that you're interested in and confirm that you get a minus sign. In particular, you'll notice I'm taking, here we go, this formula for the reflection, plugging that into the function, right? The first coordinate becomes negative y. The second coordinate becomes negative x, and you plug all that in, and this function turns into that, which blah, 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 which in fact, as required, gives you the minus sign that you need. Okay. All right, and all the rest of the stuff is details that you're not responsible for per the policy that I outlined last time. Okay, here's another example. Now this, it's right there on the page what the surprise is on this one, but I do want to talk through how a lot of students can mess this up. Very, very common for students to just crash and burn on an integral like this, because very reasonably students will look at this and see, okay, well my domain, oh gosh, let me try to draw a straight line. Yeah, there we go. My domain has these corners, which are pretty easy to write down. So you have this triangle is your domain. It basically leaps off the page at you that is, again, artistic competence. Oh, come on. There we go. Leaps off the page that that's a symmetric domain. It is a symmetric domain. That's true. And you can also look at your integrand. Your integrand y cubed is odd. You can see the oddness. It's right there in the odd exponent. That is the motivation for why we call this feature odd in the first place, right? So it's clearly an odd integrand. It is clearly a symmetric domain. And a lot of students playing a little too fast and loose with this very powerful idea of symmetry will declare this integral to be zero by symmetry. And that's not true, and it's completely irrelevant to an actual solution to this question. And so it doesn't get any partial credit because there's nothing relevant to how you would actually solve this problem. It's just a pure swing and a miss. So now why does the symmetry argument not work here? We have a symmetric domain. True. We have an odd integrand. True. The problem is the domain symmetry is over the y-axis. And if you think it through carefully, and I'm going to draw another little axis system over here, you would get the oddness by plugging in, let's see here, let me try to do this like this, by plugging in a minus sign into the y, making your y coordinate the negative of what it had been, looks like this. That's a reflection that would make the y coordinate the negative of what it had been. Notice that reflection is over the x-axis. So yes, we have the two needed symmetries, but they're not over the same line. There is no symmetry argument. This integral is not zero. Even more to the point, not only is the integral not zero, the symmetry argument fails, as of course is better. since it gives you the wrong answer. Does that make sense to everybody? Dangerous. So dangerous. An unsuspecting, ever so slightly careless student walking along on an exam encounters this and it's like, oh, boom, symmetry, 0, moves on to the next page. Please don't let that be you. You have to think through all the details. You have to be super duper careful about it. Again, you don't have to document the details. All you have to do is tell me what is the line, singular, that you're using for your symmetry, and declare that you're using a symmetry argument. Declare that the answer is 0. Right? So this integral is 0 by symmetry over the whatever line. Full credit if the argument holds water. So this one doesn't. Okay, let me pause on this for a second. How we doing? Everybody good? Okay. Good news. In 3 dimensions, it's morally the same thing. The big difference in 3 dimensions, of course, is that we don't reflect through lines. We reflect through planes. There is an attempt at drawing a picture of what it looks like when you reflect through a plane. The easiest, relatable example, physical, manifestation of this, looking in a mirror. Thus the name reflection. It's literally what you see. That's where your reflection is when you look in the mirror. Okay. So we get equivalent ideas of oddness and domain symmetry. We get a practically indistinguishable result. Right? Compare this theorem with the one that I wrote down for double integrals. I'd laid out on the page exactly the same. It's almost indistinguishable. Really, the only difference is that these are planes instead of lines, and that this is a triple integral instead of a double integral. It's exactly the same otherwise. Okay, so let's use this idea. And here we go. This is another great example, by the way. If you were to do this example in rectangular coordinates, square roots everywhere. Nightmare of just massive ugliness. Right? You could do it in spherical coordinates. Each one of these rectangular variables will then be chock full of trig, and now you're going to deal with trig nightmares. Different kind of nightmares. Right? Probably a little better than rectangular coordinates, but it's hard to see these things coming until you work them out. So here's the much better solution. Much better to make a symmetry argument. I'm going to pick the xy plane to make this symmetry argument. I'll tell you where I got that from in a minute. But for the moment, let's just see how the symmetry argument works in this case. If you're reflecting through the xy plane, here's your formula for reflection. Little geometry thinker there. Think through how in space, if you reflect through the xy plane, you get a minus sign on the z coordinate. Let's see here. Our domain is clearly symmetric because, after all, it's the unit ball, so that's easy. Right? And I claim that the function is odd because when you plug in the reflection and compute the value of the function, notice that the minus sign that you put in on the z-coordinate, as required, indeed does translate into a minus sign on the output value. And again, that's just a matter of plugging into the algebra. So this integral is 0 by symmetry through the xy plane. And again, just as a reminder, on policy, on an exam, you don't have to write all this stuff down. What you have to tell me is that it's equal to 0 by symmetry, and then you got to tell me what line or plane you're making your symmetry argument through. You give me that, and if the argument works, right, full credit. Is that all good? Okay, now as promised, let me tell you, why did I decide to use the xy plane here? Why did that seem like a good choice? Did I just kind of pull that out of nowhere? And no, in fact, the argument for where this came from is actually kind of already on the page. And here's what it is. I know that I need a minus sign on the output. And looking at this structure of my integrand, I can see that that's where the minus sign is going to need to go to result in this output minus sign that I need. Okay, so that suggests, right, the fact that I want this minus sign suggests that I want to put a minus sign there in the formula, which suggests that I want this to be my formula for my reflection. Notice I'm just kind of reverse engineering how I want the calculation to go. I want the calculation to end this way, and so I kind of need it to start that way. Does everybody see the idea there? All right, now let's just ask myself, I sure would like it if this was the formula for my reflection. By the way, just because you write down a wish list doesn't mean that it's even a reflection at all. So I have to ask first, I suppose, is this in fact a reflection? And if it is, what is it a reflection through? And so you draw a little picture of what that looks like. Draw yourself a little XYZ space here. You draw this reflection, which will take a point like that and turn it into that. And not hard to see that the XY plane is what will make that the reflection. So sometimes the motivation for how you decide what line or plane to choose, sometimes it comes from the integrand, as you see in this case. Sometimes the motivation for what line or plane to use comes from looking at the domain, right? It was, in this case, we looked at the domain and we're like, okay, well, clearly that's got to be my line or plane of symmetry line in this case. There's no single right answer. Every question's a little bit different. And choose your motivation based on what seems to be most natural for the question. Everybody happy? Okay, happy symmetry arguments. Okay, so moving along. Now, this is a weird term. I don't know if y'all noticed, but a couple of years ago, Duke changed the schedule for summer term ones, and for perfectly reasonable reasons. The unfortunate punchline is we have one fewer class meeting than most classically Duke terms have. So we have a little bit less time to work with, and I've been trying to make up for that by going maybe a little faster than usual, and that has helped some, but maybe not quite enough. You'll notice we're quite a bit behind schedule at this point. So I am going to make it a sort of an executive decision on this offering of the course, and we're going to skip section 5.6. There are some cool applications in here. They're not critical. They're kind of cool. So I'm just going to largely wave my hands at what it is that we're not going to cover and that you're not responsible for, but nevertheless you might want to be aware of, and depending on your interests you might want to read on your own. So there's this idea here of a weighted average, which by the way I think is something you may already be familiar with. If not, notice that our course grade system involves weighted averages, so that's a reason you might want to look at this anyway. And notice I have a friendly little example here showing you exactly how weighted averages work, and what we will do in this course is totally analogous, different numbers, but totally analogous to that example. So take a look at that. Then there's the idea of the average value of a function, which ends up being morally a weighted average. There's the idea of a center of mass, which it turns out is a weighted average of a function, namely the position function. And argument, that'll give rise to an example like this where we compute the center of mass of a weird shape, and I don't know why that's doing that. So here's the shape, and if I wanted to know where the center of mass of this is, by the way, probably going to be on the y-axis there. I mean, just thinking about symmetries. But we'd expect it to be about right there, or maybe a little higher, I guess. It's kind of hard to see this coming exactly. So how would you compute the coordinates of that center of mass? And we're just going to plug and chug with the formulas motivated above that. Again, y'all can read if you're interested in. So real quick for your consideration, notice that in this calculation, you can make a very easy little symmetry argument. I think it is a healthy exercise to think through those details. How do you know that this integral is 0? By way of a symmetry argument. Mathematical symmetry argument, not a physical argument about how stuff balances in the physical world we live in, right? That's not a mathematical argument. So think it through. It's a good exercise. The other coordinate, the y-coordinate down here, there's another nice little example that comes out of this that I want to draw your attention to. So there are, of course, two different ways to do your differentials. Again, healthy exercise to think through what that does for your bounds. And then you look at these, and it's kind of cool how sometimes you get lucky, and it's very hard to see this coming. You'll notice that there's square roots either way. The fact that there's 2 square roots in the upper one doesn't really make a difference. It just means that you're going to have a square root in your integrand, right? But what's kind of neat about this is this one here. Really hard to see this coming. Sometimes you just get lucky, but check it out. The very first thing that happens is you'll do an antiderivative of y with respect to y. The antiderivative then is y squared. You'll be plugging that ugly square root right into a squaring, and the square root just poofs, disappears, and you have basically no square roots to worry about. Right? So, again, it's you might as well keep your eyes open for these kinds of possibilities. How often does stuff like this arise? Well, maybe not every day, right? But often enough that it's good to always kind of keep one eye on the lookout for such lucky breaks. Okay. Alrighty. Then there's a very cool little discussion here about this thing called moment of inertia and where the formula for it comes from. And it's a cool argument, but it's a physics argument, and this isn't really a physics class. So it's a little bit of a weird thing to have included. One of the reasons why I'm feeling pretty comfortable skipping it. There is a lot of cool physics here, and I do have that physics background that makes me want to talk about it. And if you're curious, come on into office hours. I'd love to talk about this, the related physics and what this has to do with engineering, how this might possibly matter to you, depending on this and that. And I'd be happy to. But anyway, there's the formula, and if you want to be prepared for, this idea that you'll see something called moment of inertia in a future physics class, then this is the formula you should be prepared for. And then we just have here some kind of examples. Okay, so again, we're basically skipping 5.6. You're not going to be tested on 5.6. You are absolved of 5.6. But again, I just want to hit some highlights. Everybody okay with that? Okay. So off we go to Chapter 6. And y'all may recall I've been building up all semester. I've been building up. We're going to need this in Chapter 6. It's going to come up in Chapter 6 and 7. Chapter 6 and 7 is when the fun starts, right? And here we are. So exciting time. We're going to start with a new definition. Got to be prepared for stuff like this to happen. And that is sometimes your domain might be what I'm going to call dimensionally awkward. So what I mean by this, you look back at every integral we've defined. We've done double integrals. The domain was two-dimensional. And it was inside of a two-dimensional space. It was the same dimension as the world it lived in. Right? We've done triple integrals. We've talked about solid three-dimensional lumps. And they're three-dimensional, and they live in a three-dimensional world. And even back in single variable calculus, intervals are one-dimensional on a one-dimensional world. So we've had dimensionally convenient domains up to now. And now we're going to entertain dimensionally awkward domains. So for example, let's think about this right here. Right? We have a one-dimensional, let me do it like this. We have a one-dimensional curve, but notice that it lives inside of a two-dimensional plane. That's weird. Right? Let's try and fail, by the way, but just to see what the experience is like, let's try and fail to imagine some sort of maybe I want to compute the mass on that curve, something like that. How would I compute that with my existing integration tools? Well, we're in the plane. It's a two-dimensional question in some sense because it's a two-dimensional world. Can I compute this with a double integral? No, there's no area. The domain has zero area, right? So that doesn't work. Okay, so the domain is sort of intrinsically one-dimensional. Can I use my previous understanding of single variable integrals to add up this mass? No, because that would assume that my domain's just an interval. It's not. Look at it. It's all curvy and stuff. So our existing Riemann sums, our existing notions of integrals, they just don't fit. And we are out of luck. That make sense? Okay, well, how are we going to do this? How are we going to deal with this? So here's the big idea. Even though we've adapted the idea of a Riemann sum to single variable integrals, double integrals, triple integrals, this is a different sort of a situation. We're just going to tailor a brand new kind of Riemann sum to address exactly this situation. And you can almost probably guess how this is going to work. We're going to take this whole and break it up into pieces, as we do with every integral we've ever seen. You take the domain, you chop it up into little pieces. There you go. Then, just like every integral we've ever seen, we're going to look at one piece at a time. And on each individual piece, we're going to talk about stuff per unit size times size. Right? So, what's the notion of size that we're interested in here? Well, on this little piece of our domain being a curve, this little piece of curve has a length. So our corresponding stuff per unit size is stuff per unit length. So for example, if I wanted to compute the amount of mass distributed over this curve, the calculation I have in green, applying to each little piece, would just be mass per unit length times length. If this wire, perhaps this curve were representative of a wire stretched out in the plane, and maybe there were little ants crawling on it, right? If I knew how many ants per unit length there were, I could do this construction. Ants per unit length times length would give me ants, and I could count the ants. That make sense? So it's dimensionally different. There are some scary questions facing us, like how in the world am I going to compute this? Right? All of our computational rubber meets the road, how do I get an answer, involves relating to single variable integrals, like iterated integrals. Right? So can I relate this to something kind of like an iterated integral? We'll worry about that in a minute. Right? But just to get our hands on the question, just to turn an abstract question into some mathematical notation and a strategy for how to add things up, this does it. Stuff per unit size times size. How are we doing? Everybody happy? All right. Okay, so here's the notation that we'll use. We're going to represent this with this, and you can kind of notice the pattern. As with every other integral we've ever done, we represent, the little deltas with differentials. We represent limits of sums with that symbol. Whatever the integrand is, that comes along for the ride. And whatever the domain is, let's see, I'm out of colors. Red, okay. Whatever the domain is, right, that domain is indicated as a subscript. So, frankly, it's exactly the notation that we really kind of ought to expect. It's right there with the pattern of every other integral we've ever defined. Is that cool? All right, so a case could be made. This ought to be called a curve integral because it's an integral over a curve. You could imagine maybe it should be called a path integral or something like that. And some people do, in fact, call them path integrals. It's much less common terminology. The much more common terminology is line integral, and, it's not a straight line, right? In the common mathematical usage, the word line means straight line. That's not what we're talking about here. This is line as in like a line drawing. In other words, a curve. So anyway, maybe a little bit outdated terminology, but that's the common terminology. Okay. Now, why do we call this a scalar line integral? What's the deal with this, clarification? And I am going to punt on that one for the moment. Later, possibly today, we're going to see a different kind of line integral. A really structurally different circumstance where we're still looking at a curve, we're still chopping up the curve into little pieces, but we're going to end up, because of the different scenario that it will be, we're going to end up with something that's really importantly different from this. And so this word scalar is to distinguish it from that soon to becoming different idea. Okay. All right. So anyway, for the moment you can call it a line integral, but I'd prefer scalar line integral. You'll note the book also calls it scalar line integral. Okay, how to compute these things? Well, I have good news. We basically already have all of the tools that we need. We just haven't noticed yet. So here we go. We're going to notice. When we have an undesirable domain, we've already kind of developed a broad outline for how to deal with undesirable domains. You do change of variables. We love change of variables. I can turn round, curvy things into straight, convenient things. We can turn discs into rectangles. It's nice, right? Get rid of all those ugly square roots. How does change of variables work? Well, you take your domain, you take your undesirable domain, that is, and the very first thing you have to do is you have to view it as being an image. So I'm going to need to figure out how to view a curve as being outputs from a function. And again, good news, we already know how to do that. That's called a parameterization. We've already talked about parameterizations. We've given a name, parameterizations. We've studied techniques for how to create parameterizations. We already had it. Lucky break. Right? Sometimes you get lucky. Okay. Once you have your undesirable domain viewed as an image, then of course we make a pullback argument, and the pullback says I'm going to turn an integral on my undesirable domain into an integral on my pullback domain in green over there. And of course all I have to figure out to make that make sense is I've got to figure out what the stretching factor is. So I'm going to need, now getting rid of my mess, I'm going to need to know, given some little dt, how would I ascertain the resulting ds? What is it that I multiply by that input size to get that output size. How much bigger is that little piece of output than that little piece of input? Well, keeping in mind that dt I think of as being a little piece of time, and ds is a little piece of distance. What's the relationship between distance and time? Well, speed. So there's our stretching factor. That's what I put in there to rewrite ds in terms of dt. It's just the speed. And speed, of course, is the magnitude of the velocity, which the velocity is the derivative of the position. So, boom. Is that cool? So we're there again. We already had all the pieces. We just had to notice we had the pieces and assemble them. And as such, ds, stretching factor times dt, stretching factor known. The function, you just plug in your parameterization. Keep in mind the parameterization there, x is a function of t, tells you literally how to rewrite x and y in terms of t. Right? So just plug that on in. And happily, we now have an integral pulled back onto our new domain here on the t-axis, and this becomes a plug-and-chug question. Okay. All righty. So parameterize, and don't forget your stretching factor. Okay, so here's a quickie little comment that needs to get made. There is something a little disconcerting about this formula. Notice that in this formula here that we're going to use to compute integrals, these scalar line integrals, notice that the parameterization is in there a couple of times. I also recall that parameterizations are not unique. There's lots of ways to parameterize a curve. What if I parameterize it with one parameterization and you parameterize it by another parameterization? We're going to have different integrals. How do I know mine's going to get the same answer as yours? You wouldn't immediately think that two different integrals would give you magically the same answer. Very satisfyingly, they do. So this integral is independent of your parameterization. So parameterize however you like, it won't make any difference. Always get the same answer no matter what parameterization. So, thankfully. Okay. Said differently, don't worry about it. Okay, so here's an example. This is actually a bunch of examples. We're going to kind of do a bunch of examples all at the same time here. And in particular, I have the following setup. There's a wire of non-constant density. And it's following a path parameterized like so. Here's the non-constant density. There's now various questions that I can ask about this wire, right? So I have mass distributed over a curve in a certain way. I can ask how much mass there is. I can ask what's the location of the center of mass. I can ask what's the moment of inertia of that thing around a certain axis. Various different things that I can write down, various questions I could ask about the same wire, parameterized by the same curve, with the same distribution of density. Okay, so the very first thing I'm going to do to all of these questions is notice that they're just different integrals. They're different scalar line integrals. They all use the same parameterization. That means they're all going to have the same velocity vector, which means they will have the same speed and therefore the same stretching factor. All that's the same. And so this calculation that I've done here to get this stretching factor, that's going to apply in all four of these examples. Furthermore, don't forget parameterizations. Let's see here. Parameterizations are literally telling you x and y as functions of t. So not only am I going to be plugging in the same stretching factor, I'm going to be plugging in for all 4 of these examples the same formula for x, the same formula for y. So different computations, but they're going to share so much. I can kind of do them all in parallel. Let me just point through the details for a couple of these. Starting with, let's see here. Let's. How do I write down mass? Well, mass, the whole is the sum of the parts. Mass is density times size. So I get this integral. Now, parallel computation over here. I have a different formula for the x-coordinate of center of mass, copying from the previous section. It's a different integral, but again, I get kind of this same deal in the same way that dm is density times ds there. Well, yeah, dm is density times ds here, too. So that part of it is dealt with the same way. Okay, that stretching factor allows me to rewrite the ds in terms of dt. Same stretching factor. Fits in the same way for both integrals. Is that cool? All right. Likewise, now again, don't forget, we have a formula up here for x. We have a formula up here for y. And with that in mind, coming down to these integrals, this y right there, t squared. This y right there, still t squared. Because it's the same curve. We're asking different questions, but it's still the same curve. We're using the same parameterization, and therefore we have the same formula for y, and likewise the same formula for x as well. So the way we develop these integrals is just, it's, oh my gosh, so much overlap. Okay. So now, of course, you got to compute these resulting integrals, and that integral's a little ugly, and this is looking a little ugly as well. We're not going to compute those. By the way, y'all probably noticed, but on my old exams, there are a lot of questions that say here, set up the integral, but don't evaluate it. Right? And that's what I like to do when the resulting integral is actually going to be a massive pain. And my motivations on exams, right? My motivation is to see how good you are at multivariable calculus. I have only a slight interest in how good you are at single variable calculus. Obviously, I need you to be competent with single variable calculus, right? But I don't want you to have to spend half of your exam cranking out single variable calculus. That works against my incentives, right? So I will sometimes have questions that say, don't evaluate the integral. Okay. Alrighty. Here's another example. This is just a little different. So a little bit more sort of odd, I guess. So here is a fairly real world kind of problem. I'm building a fence. I'm fencing off a circular plot of land for whatever reason. And I need to compute the area of the fence. And by the way, why do I need to know the area of the fence? Well, maybe I'm hiring somebody to stain the fence. And he's given me a quote for how much he's going to charge me to stain the fence. And the quote's based on the area. I've got to make sure he figures the area right. Right? If he figures the area the wrong way, then I could accidentally get overcharged. And by the way, I've avoided several possible instances of being overcharged by using my math.
It's a nightmare.
Yeah.
Like, here's your estimate, and you're like, no.
Yeah.
This is my triple integral I done.
Yeah. Absolutely. Yeah, not triple integrals exactly, but I have snuck up on some cheaters and caught them. Yeah, for sure.
That is a good real world application.
I'm saying, yeah. Okay, so anyway, here we go. How are we going to do this one? I need to know the area of the fence. Well, the big first idea is to recognize that we're doing an integral on the curve that the fence is sitting on top of, because if I were to look at a little piece of this curve, such as, let's take that little piece down there, for example, well, as you're moving along, here's your fence, right? And if I were to break up the curve into little pieces, for example, if I looked at little pieces of curve of size ds, I can talk about what the height is at that location on the fence. And right there in the picture, height times length gives me area, right? So this area, oh, that yellow doesn't show up very well, does it? Let's see here. We'll use, what am I going to use? Red, I guess. That little piece of area there, height times length. Is that cool? And if I just add that up then over the entire footprint of the fence, namely if I add up over that entire circle, that will give me the total area. And don't forget to multiply by 2 because you're going to want to stain both sides of the fence, right? Okay. All right. Okay, so we've written down, this is what you might call phase 1, right, of the calculation. We've written down a, in this case, scalar line integral, aka a Riemann sum. We've written down our Riemann sum to represent our application. The next thing I need to do is turn this into a single variable integral that I can actually get my hands on. And so here's where the parameterization comes in. The parameterization, we need to know how to parameterize the unit circle. No problem. Old news. That was our very first parameterization way back when, like second day of class or whatever. Okay, well, I'm going to need to know x prime apparently, so I just take the derivative to get x prime, and then I take the magnitude to get my speed, and notice that's exactly what I need, right? Speed is exactly what is needed to turn distance into, to rewrite distance in terms of time. Note further, let's see here, let me get through it. Okay, there we go. How am I going to deal with this x right there? How do I rewrite x in terms of t? This is one of the parts that students very often kind of forget. Again, the parameterization does it for you. The parameterization is right there, explicitly telling you how x is a function of t, and so you can see that simplifying right there. And so, all together, step 1 was to turn my application into a scalar line integral. Step 2 is to turn my scalar line integral into a regular old single variable integral. And then step 3, plug and chug, answer. So structurally, again, pretty similar to previous kinds of integrals we've seen. Different details, different sort of, intuition, different physics, different geometry. Same basic ideas. How we doing? Okay. Oh, right. Don't have a... Okay, good. All right. Oh, and I forgot to turn my ringer off. Sorry. Let's head that off before I get in trouble. Okay, so here's another example, or so we are going to think at the outset, and then something weird's going to happen. Okay, so maybe I've got a path, and I want to add stuff up over a path. We're instantly thinking line integral, right? Scalar line integral. Yeah, you'd think. So, this time we're doing a different calculation. We're not computing mass. We're not computing area of the fence. We're not computing a center of mass or anything like that. This time we're going to compute work. And y'all will probably recall we have an old formula for how to compute work. But work assumes that you're moving in a straight line, which in this case we are not. Right? This formula we have up here from Chapter 1 assumes you're moving on a straight path. We are not in this case. By the way, furthermore, this formula up here assumes that the vector field is constant. And check it out. The vector field is wildly non-constant. So we do not have a constant force as we would need. We do not have a straight path as we would need. How are we going to compute work now in this non-constant, non-straight, weird scenario of, which by the way is very real world. This is how life is, right? How often is it that your path is perfectly straight, right? So, okay, all right, so natural question. As you might expect, I don't know why that's not deleting. What's going on? Oh, my pen died, that's why. Okay, hang on a second. Sorry, I got to plug in my pen. I've never really quite figured out why sometimes it runs out of charge and sometimes it doesn't. Okay. Right, so what are we going to do? Well, as always, we're going to chop it up into little pieces. Each piece is approximately straight. Each piece is small enough that the force is approximately constant. This makes, on each little piece, the job becomes simple. So again, on, for example, this little piece right there, teeny tiny little piece. I'm not looking at the whole curve all at once. Don't try to be a hero and do this all at once. On each little piece, it's a relatively simple problem. Basically straight. Round off errors are going to go away in the limit. The force is approximately constant. Round off errors are going to go away in the limit. Is that cool? Right. Now, here's the problem. There is something fundamentally eyebrow-raising about what we're looking at here. I don't know if you've had this instinct that this is fundamentally different somehow. But real quick, let's look back at our previous examples, like this area. If I'm staining this fence, will I use more stain if I go around and stain the fence counterclockwise versus clockwise? No, it's the same fence. It's the same area. Go whatever order you like. Who cares? It literally does not matter which direction you're going along the curve. If I'm interested in computing the mass of this wire, will I get a different answer if I add them up one way along the wire versus the other way? No, of course not. The mass doesn't depend on the direction at all. What about the work? If this is a mountain road that I'm driving along, and if the force represents, in some sense, how much force I have to, because it's steep, right? And gravity is pulling me downhill, right? If the force represents the gravitational pull, which is going to be in different directions, depending on what the shape of the hill is, wherever you might be, is the work the same, whichever way you drive the road? Oh, very much no. It's a lot more work to drive up the mountain than to drive down the mountain. Yeah? By the way, are you all aware of this thing called electronic braking on hybrid cars and electric cars? Super cool idea. Basically what they do is they turn the wheels of the car into little electric generators. I'm sure you've heard of electric generators, right? That idea's been around for nearly 200 years at this point. And if you can apply enough force to turn a crank, then there's clever things you can do with coils and magnetic fields and stuff like that, and you can make a light bulb turn on just from the mechanical, right? So it turns mechanical energy, rotational mechanical energy, into electricity. And that's how electronic braking works pretty much, right? They take the fact that the wheels are rolling and they turn that rotational kinetic energy into the electricity of charging your battery of your hybrid or electric car. So if you drive uphill up a mountain road, you will deplete your battery. And then if you then just ride the brakes all the way downhill, that will recharge your battery. It's very, very clever. And I don't know if the efficiency is perfect. It's probably not. You'll still take a little bit of a ding. But, I mean, in the abstract, friction aside, right, it should work just right. So fun little digression. But so the point here is that you definitely get different answers depending on which way you go. This is different. This is not how scalar line integrals work. Scalar line integrals, mass, area, go whatever order you like. Who cares? Something's going on here. Okay. So in particular, to even ask the question, when I say, I've got a force and I've got a curve, how much work does it take? Not really quite good enough of a question. I've got to indicate which direction am I going along the curve. How much work? Well, do you want me to drive up the mountain or down the mountain? You've got to specify the direction on the curve for the question even really fully to make sense. And so when you have that included, we call this an oriented curve. It's a little bit more than just a curve. It's a curve where you indicate which direction is the direction you're going. All right, let me pause on that. It's a little bit of a weird idea. Is everybody on board? Okay. All right. Let's see if my thing is back in business here. Nope, not yet. Okay. Wait, is it? Nope. Okay, let's see here, moving along. Okay, so with that in mind, we can write some stuff down. Let's, again, think about one little piece of curve, perhaps like so. How would I compute the amount of work that it takes to move along that curve? Well, as previously discussed, we're basically talking about a straight movement with a constant force, and so it's just force dot displacement. Well, my force is given. F is my force. And I need to dot that with my displacement. Well, my displacement, we already have a name for our linear approximation of displacement along a piece of curve. Flashback to chapter 3. You'll recall back in chapter 3 we set up and defined various things like the dx vector. We defined the unit tangent vector, the ds scalar, all that stuff we defined back in chapter 3. So that dx is my displacement. Force dot displacement will then tell me right away that the amount of work that it takes to move along that piece of curve, it's just force dot displacement. And so I tell you what, I'm just going to write that down. Work is force dot displacement, adding up over the entire curve. Grand total, my grand total amount of work is expressed like that. Everybody follow? Notice it doesn't look like a scalar line integral, does it? It's different. It's importantly, it's different in a couple of ways. A little bit of which is disturbing and scary looking. So in particular, let's see here. There we go. Okay. There we go. Okay. So in particular, I am somewhat creeped out by the fact that I've got a differential that's a vector. We've never seen an integral with a differential that's a vector. What is that all about? How are we going to deal with that? So anyway, I just want to acknowledge the creepiness. Right? Another disconcerting thing. My integrand is a vector. Now, we did see one example of that a long time ago, but still pretty weird to have an integrand that's a vector. Every integrand we've seen in the past has been a scalar, very often a density, for example. Stuff per unit size, it's a fundamentally scalar thing, right? That's not. My integrand is a vector now. So anyway, this is why we call this a vector line integral. It's because it's made up out of vectors, integrands and differentials, instead of scalar integrands and differentials. And thus the need to distinguish scalar line integral from what we're going to call here a vector line integral. Is that believable terminology? Alrighty. Oh, by the way, while we're here, I'll point out, here's another sort of disturbing thing. Check it out. That's a dot product, right? When have we ever seen an integral where there's dot product in the basic notation for the construction? Also weird, also new, also never seen before. And that, of course, is a vector operation. Okay. Now, all of this is pretty natural, of course. All of that vectory stuff comes out of just, well, look at what we're computing. We're computing work. Work is, on little things like this, a dot product of vector forces and vector displacements. It's not hard to see where it comes from. It's just unsatisfying what the result is. Okay, all right. So now how are we going to compute these things? Again, we face a situation like, when we were looking at scalar line integrals for the first time, right? We had to figure out how to turn something like that into an integral we could make sense of, and we viewed it as an image. We interpreted the appropriate pullback. We reasoned to figure out the stretching factor. Boom. So we're going to do kind of the same thing here. It's just different details. In this case, the details, again, are pretty convenient. No big deal. In fact, arguably even more convenient than we had with scalar line integrals, because we have pre-existing rewrites of the dx vector. Right? So this dx, okay, well, I can write it as x prime dt, or I can write it as capital T ds, whatever. And there it is. Right? So when you want to compute, for example, the amount of work that it takes to blah, 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 and you write down a vector line integral, how are you going to compute that vector line integral? Well, here's your formula. Right there. Everybody okay? And by the way, here's another formula. This one over here, it serves a purpose. This last one. It serves a purpose. A lot of people like that notation. I am a little unthrilled about this notation. Like I say, it serves a purpose. You have to be aware of it. You can't not know this. Right? You definitely need to know this notation. But my own personal preference, vast majority of the time, I like this one, and I'm kind of meh on this one. So the main complaint I would make about it is as follows. Notice this writes the differential as a ds. The ds is multiplied by a scalar. Now the scalar is computed as a dot product. Yeah. But nevertheless, the integrand is a scalar quantity. It makes this look like it's a scalar line integral. And I think it's important that when things are different, we shouldn't try to conflate them. Right? Now that's my position. I think that makes sense. When you have things that are importantly different, conflating them is counterproductive. Right? Right? So to me, this notation is toward conflating things that are importantly different. This notation here, a little creepy when you first write it down, right? But it is recognizably distinct as I feel like it should be. So anyway, that's one of the reasons I like this notation, and I won't go on. There's a lot of other reasons I like it. Oh, here's a quick one. It's the shortest one to write down. The fewest pencil strokes. That's got to count for something, right? So anyway, there's various other reasons I like this, and I'm going to let that all slide. Okay, so let's do an example. Here is a real-world problem. I am walking counterclockwise along the top half of the unit circle, and as I walk, there is a force being exerted onto me. And in particular, there's wind blowing at me. And if you think it through, if there's a force applying to you this way, then you have to exert an opposing force the other way so that it doesn't blow you over, right? Most of this is kind of subconscious. You don't consciously think about it. No one would just stand there and the wind starts blowing and they're like, uh-oh, here it comes, and then they just fall over, right? You naturally lean forward. You're naturally pushing. Well, of course you do. Nevertheless, conscious or otherwise, you are exerting a force. So the big question is, as I walk along this path, exerting a force as I must, how much work am I performing? Does everybody see the question? Okay. Well, this is a tailor-made question for the construction that we just wrote down. Reminder, I was given... let's see, let me make some good color choices here. I was given that the wind is exerting this force on me. This thing called F is what the wind is doing. I have to exert an opposite force. So the force that I push with, relevant to computing the work I am performing, right, is minus F. Is that cool? Okay, so off we go. We're done with phase one, right? We've taken an application question. We've written it as a Riemann sum, aka an integral. In this case, a vector line integral. And now we got to figure out how to do a pullback. This is just a matter of noticing that we have, again, a pre-existing parameterization. I guess I should not get too ahead. Counterclockwise, top half of the unit circle. The fact that it's only the top half, by the way, is why t only goes from 0 to pi. So there's my parameterization. Easy to take the derivative. Bad colors. Easy to take the derivative. So there's my velocity. Now I'm good to go on using this formula right here. If you have a vector line integral, f dot velocity dt. So we write that down. Here we go. Okay. So, colors all over the place. My force dot my velocity. Missed. Sorry. Dot velocity dt. Let's see here. T goes from 0 to pi. So my bounds 0 to pi. Just plug it into the formula. Is that cool? Okay. Alrighty. Let's see here, and now it's computation time. Okay, well, let's see here. We did compute x prime already. That was that. The field that was given to us, the vector field that was given to us is this. Don't forget, we need the negative. So gotta, don't accidentally drop that minus sign. I mean, you can multiply it in elsewhere in the expression if you want, but don't forget about it. Recall, furthermore, and this is another one that's easy to forget, but the parametrization gives me my x and my y as functions of t. So let me, by the way, do this. So x says right there is cosine t. So that x, cosine t. All the minus signs. By the way, it's real easy to mess up these minus signs. I strongly urge you to be slow and careful with your management of minus signs. It's real easy to mess it up. So notice what I did there. I'm not trying to deal with minus signs and plug in other things and something else all at one time, keeping everything in my head. I do not trust myself, and I encourage you not to trust yourself on that either. And then let's see here. Likewise, y is sine t. Right? So it's just a matter of plugging it all in, and as we expected, we've ended up with a single variable integral. In fact, it's a pretty easy single variable integral, and there you go. All right. Happy? All right. Does the parametrization matter? And you're expecting me to say, nah, parameterization does. Oh, yeah, sorry, question. Yeah, go ahead.
Last example.
Yep.
Isn't that just pi is just the distance you walked, right? Why is that the same value?
Coincidence?
Okay.
Yeah. So, I'm just going to leave it as coincidence. Yeah, sometimes that's just how it happens to turn out. Roughly speaking, the point here is that I'm in the wrong mode. These vectors are parallel, and this one has unit magnitude, this one has unit magnitude, and so it's just kind of a coincidence.
Okay.
Yeah. I could have made the question like a little bit hairier by including some different constants and some weirder curves or whatever, but I wanted to keep the focus here on the method and not on hairy details.
Okay.
So yeah, that's right. Is that satisfying? Okay. Right. Okay, so when we were first looking at scalar line integrals, the computation of the integral was independent of the parameterization. So knock yourself out, do whatever's most convenient. Doesn't matter, go crazy. You would hope that would be the case here, and it's not. And we've already seen why, because the direction matters. Right? You have to parameterize the direction that your oriented curve is going. And again, one thing that's really important about questions like this, the domain is technically not just a curve. The domain is an oriented curve because the direction matters. Right? So don't be too casual about how you parameterize. You do have to parameterize the correct direction. And if you don't parameterize the correct direction, you're going to have every single step that you'll be taking will be going exactly the wrong direction. Here's the beautiful thing about exactly wrong. It's consistent, and it's consistent in a very convenient way. So if you are going exactly the wrong direction, if your dx is exactly the negative of what it should be in every term in your summation, well then the total is going to be off very predictably by that exact same minus sign. So now this looks like a way to document mistakes, and kind of is, but it's also a pretty clever tool that you can use. And so in particular, we're going to define here the idea of taking a curve and orienting it opposite of the way it's supposed to be. A little superscript with a minus sign. That's how we're going to denote the same as the curve C, except going the wrong direction. And as we just discussed, if you go backwards, you will get the negative of the answer that you would have gotten if you'd gone forwards. So, again, you can think of this as a way of telling you how wrong you're going to be if you parameterize the wrong way. On the other hand, you can view this as, hey, if you decide for whatever reason, possibly even a good one, to parameterize it the wrong way, no problem. You're just going to be off by a minus sign, and if you're willing to account for that later, cool. Right? No problem. Just don't forget to account for it appropriately. Let's see how we're doing on time. Okay, that's actually a pretty good place to leave it. We will draw the line right here. We will pick up on this on Tuesday with some examples. And good luck to everybody studying for the exam this weekend. I'll be writing the exam this weekend. See you on Monday. Oh, hang on just 1 second here. Let me get the...